Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at similar matrices. So two matrices A and B are said to be similar if there exists an invertible matrix P such that A equals P, B, P inverse. So it turns out that if two matrices are similar, they have the same trace, determinant, and eigenvalues, but not necessarily the eigenvectors. Now we are really interested in when we can find a matrix A that is similar to a matrix here that is diagonal, because as we will see, that will really help us calculate powers of matrices much more efficiently. But first we have to understand what's meant by a diagonal matrix. So a diagonal matrix is one where all off-diagonal entries are zero. So in a diagonal matrix, the entries along the leading diagonal can be anything you want. They can be zero, they can be non-zero, but the entries off the leading diagonal all need to be zero. This is a diagonal matrix. This is not a diagonal matrix because it has an element here that is not on the leading diagonal and is non-zero. So the only way a matrix is diagonal is if these off-diagonal entries are zero. Okay, what's with all the fuss about diagonal matrices? So what is with all the fuss about diagonal matrices? Well, raising a diagonal matrix to a power is actually really easy, and that can help us raise other matrices to a power. So here what I've done is I found a matrix and it is similar to a diagonal matrix. So A is P, D, P inverse. Let's say I want to raise this matrix to a power. Let's say to the power of 4. It turns out if I know that it's similar to a diagonal matrix, if it is in this form, all I need to do is raise the diagonal matrix to that power. But that's actually really simple. If I want to raise a diagonal matrix to a power, all I need to do is raise each of its elements to that power. 4 to the power of 4 is 256. Negative 1 to the power of 4 is positive 1. See, this here is much easier to calculate than raising this to the power of 4. If we had to do this by hand, we would have to go through 4 iterations of multiplication. So that would take us a long time. Imagine if we wanted to raise this to like the power 20 or 30. It's actually really hard to do. In fact, this way is so much more efficient that most computer programs, if they're raising a matrix to a power, they first make it in this form and then they raise the diagonal matrix to this power. So if I multiply together these three matrices, I get this. So here you're just multiplying three matrices together, and it's a lot easier to do when it's in this form. But as I mentioned, the higher this power is, the much more time you save by putting it in this form. So let's actually look at taking a matrix and decomposing it into this form. So that process is called diagonalization. When you take a matrix A and you write it in this form where D is a diagonal matrix, you have been said to diagonalize A. Now, most but not all matrices are diagonalizable whether or not they're invertible. So whether or not it's invertible has nothing really to do with whether or not it can be diagonalized. Most matrices can be diagonalized. We won't look too much at the ones that can't. So how do you find A in this form? Well, it's actually not too hard. D is a diagonal matrix. The entries on its diagonal are the eigenvalues. And P, its columns are just the eigenvectors. We need to make sure these line up, and I will show you what I mean by that. So let's get started on diagonalizing this matrix here. Our first goal is to find the eigenvalues of A. So remember, they are the solutions to the determinant of A minus lambda I is equal to 0. So remember, A minus lambda I, you just subtract lambda from the entries on the leading diagonal. So the determinant of this matrix now, AD minus BC. So BC is positive 2, we just have a 2 there. So let's go ahead and expand this. I get lambda squared plus lambda minus 2 is equal to 0. So factorizing, I get this. The two eigenvalues are -2 and +1. What that means is the diagonal matrix D, it'll also be a 2 by 2 matrix. I just put these eigenvalues on the leading diagonal and all the other entries are 0. I found what D is. Now I need to go and find what P is. To do that, I need to find the eigenvectors of A. So for the eigenvalue -2, I want to solve A, which is my original matrix here, times by some vector, I'll just call it x and y here, equals eigenvalue times this vector. Okay, so if I go across by down, it doesn't really help us. I just get -2y equals -2y. It doesn't really help. But what about row 2 by column 1? So there I get -x minus y equals -2y. If I'm adding y to each side now, I get -x equals -y, or x equals y. So I can choose an eigenvector, 1, 1. X and y, the two entries need to be equal. Okay, so that's all well and good for lambda equals -2. What about lambda equals 1? So in that, I want to solve the equation A times by my vector, again I'll just call it xy, is equal to 1 times that vector. So 1 times the vector is just itself. So if I go across by down, I get 0x minus 2y equals x. So x is equal to -2y. I'm just going to choose a vector where x is -2y. So if y is 1, x must be -2. So these are my two eigenvectors. So when I set up P, I make each of its columns one of these eigenvectors. Now I have to be careful because I listed the eigenvalue -2 first in D, the first eigenvector needs to be the one corresponding with lambda equals -2. So that was the eigenvector 1, 1. And then this one was second, this eigenvalue was second, so its eigenvector is listed second. So this will be P, so P inverse, so remember it's 1 over the determinant is 1 minus -2, the determinant's 3, so it's 1 over 3, switch the entries on the leading diagonal, change the sign of the other two. So we have found that our original matrix A is P, D, P inverse. And D is a diagonal matrix. That means if I want to raise A to any power, I can just leave these two matrices alone and multiply by this raised to that power, which is so much more efficient. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.